Hello.
Good afternoon.
Welcome to Kotlin Under the Hood, or what is Kotlin doing down there? We had a talk that we gave
a long time ago.
DroidCon, I don't know, a year ago or something, called Kotlin Under the Covers, and someone decided that Kotlin Under the Hood would be more appropriate or polite or something, but we still kind of like Kotlin Under the. It doesn't actually matter what we call it. Let's learn some things about Kotlin. I'm Chet Haase. I'm a developer advocate on the developer relations team on Android at Google.
And I'm Romain, and I manage the Android Toolkit team at Google.
We are using Kotlin a lot more for Android, both for our external developers to write their applications, as well as internally for writing some of the libraries and APIs that we offer in Jetpack, among other things. And we thought it would be interesting to take a look at some internals of Kotlin.
So before we get started, how many of you use Kotlin already, or have learned Kotlin? All right, that's good. So for the few of us who are not using Kotlin, it's going to be just a quick recap of why is Kotlin so great, and why did we decide to adopt it as one of the officially supported language on the Android platform a couple of years ago. So that's just Chet trying to show that he knows Kotlin.
That was the first line of Kotlin I wrote.
So the first thing is that Kotlin is a more concise language. There's a lot less boilerplate, which makes code easier to write, easier to maintain. There's a series of powerful extension libraries. Some come with Kotlin itself. It's a Kotlin standard library. They extend existing Java APIs. We also provide for Android a number of Kotlin-specific extensions that make Android APIs much easier to use and much nicer to use with Kotlin. One of the main reasons we were really interested in the Kotlin programming language for Android is because of the really good interop story with existing Java libraries, and it goes both ways. So for us, the entire platform offers Java APIs, and you can invoke them directly from Kotlin without any issue. We can also provide Kotlin libraries that can be used by Java developers, so we don't want to move everybody to Kotlin. Those of you who want to stick with Java can and should. But if you want to use Kotlin, of course you can. There's a number of modern language features. We're not going to go over the entire list. There's a great website for that. And it's continuously evolving. It's actually evolving at rapid pace. So just last year, we had Coroutines and a few other features that we're going to see in this talk.
But in some respects, Kotlin is kind of magical, and it's not clear what it's doing under the hood or how it can even do that. Right, so it's based on, it goes through the JVM on desktops and on servers. It's compiling down to class file code. So how does it do that? Like if Java programming language does not offer that feature, then how can Kotlin actually handle it? And we're going to find out how that works in various instances today. But before we dive in, I was curious, how many people in the audience actually use are Android developers right now? Okay, I count 8. All right, it's fine. You don't need to. We are talking about Kotlin from an Android perspective. Some of the tools that we'll talk about are Android specific, but it's all generic information about Kotlin.
And there are equivalent tools available on server or desktop.
All right, so today we're going to learn how some of these magical Kotlin features work, and we're also going to learn how do you figure this information out, because to us as engineers, how do you actually get that information is sometimes even more interesting than what the information actually is. That's why we're engineers. We engineer things. We're going to change the order, though. Let's learn about this in the other order. So let's start out with tools.
All right, so we're gonna to understand how Kotlin does what it does. There were a couple of things that we're using. First, we looked at the bytecode generated by the Kotlin compiler. There's also a feature in IntelliJ. We'll see how it works, Java decompilation. So if you don't want to look at Kotlin bytecode directly, you can decompile the bytecode back to Java code. So for those of you who are more familiar with the Java programming language, that might be an easier way of understanding how things go. Also, some of the features we're going to look at generate a lot of bytecode. So in those situations, even if you understand bytecode, it's a lot easier and faster to go through Java decompilation. And finally, we use the memory profiler available in Android Studio. And like I said, there are other tools available on server and desktops that do the same thing. This is just the tool we provide for the Android platform, but it doesn't do anything that's very Android specific. So here's a very simple example. Again, for those of you who know Kotlin, there's not going to be anything surprising. But if you have a var called I0 and you assign 5, the Kotlin type will be int, and the Java type will be a lowercase int. So it's a primitive type in both languages. If you specify the type directly, you don't use type inference. We're in the same situation. It's a capital I int in Kotlin, and it's a lowercase int in Java. Now, Kotlin has support for nullability, so you can specify that a type, a particular variable, can be null or not. So if you say that the type is just an int, that value cannot be null. But if you say that it's an int question mark, then the value can be null. So for Kotlin, this type is the int question mark. And in Java, it translates to capital I integer, because it has to be an object to be able to hold the null value. So it's interesting here because Kotlin, at a semantic level for the programmer, doesn't make a distinction between primitive types and object types. But if you look at bytecode, the difference appears. And depending on the kind of code you're writing, or if you're writing something that's very GC sensitive, that might be something you might that you might want to look at.
So let's take a look at some bytecode. There's some. What we actually mean by bytecode is taking a look at what it looks like in class file bytecode. So in Android Studio, again, if you're not using Android Studio and not developing
Android. That's also true in IntelliJ.
Oh, true. IntelliJ, same way of getting there. So there's a menu item up there. You go up there and you say, I want to see the bytecode for this thing, and then a viewer pops up over on the right. So wherever your cursor is on the left in the editor, when you're looking at Kotlin code, then that same code snippet will be highlighted on the right, and you can see the bytecode that it applies to. If you want to use command line tool instead, you can use Java P.
Actually, sometimes you may have to, when I was using the Kotlin bytecode viewer from IntelliJ, with Coroutines, hopefully they fixed that bug since then, but as of a few months ago, it was throwing the decompiler into an infinite loop. So the only way to look at the bytecode was to use the command line tool.
I like the idea that the JetBrains tool was confused by the Kotlin language. All right. So let's look at the bytecode for the examples that we were just looking at. So we have this var, and we're going to set it to 25. We're going to use type inference to figure out what it is. The bytecode looks like this. We're going to do a byte push extended to an int onto the stack, and then we're going to store that in the first variable. In the first integer variable. For the second one, where we said, I want you to use this specific type, no type inference, it's going to be a capital I int with a value of 78. We're going to push the byte of 78 extended to an integer onto the stack, and then pull it off and put it into the second variable. And for the third one, where we have this nullable int type set to 14, we're going to, again, push a byte extended to an integer onto the stack, and then it gets a little different. We're going to invoke static. We're actually going to call a method value of, which returns an integer, which looks like this. So value of takes that int value in, that primitive int type in, and then returns a boxed value of integer back. And then we're going to store that not as an int on the stack, not in an int variable, we're going to store it in a reference variable instead. We're going to do an A store. All right, so that's the bytecode approach. That is one way to figure this stuff out. But
what if you don't want to read bytecode, not assembly code, Chet? So like I said, you can use the Bytecode Decompiler. So here's an example of that Kotlin code we just looked at. And in that bytecode viewer that you can use in IntelliJ, there's this very obvious button at the top called Decompile. And if you click on it, it will produce a new tab in the editor containing a Java version of that code. It doesn't always work entirely right, and sometimes it won't show you everything that was generated by the code, but most of the time this is just a very easy way of understanding what was going on.
Indeed. But what about the memory profiler? So this was the third tool that we mentioned. We could look at bytecode, decompiled bytecode, or we can look at what's actually happening in the heap. To see what's going on. So a memory profiler is useful for tracking what's going on in the memory over time. You can see how big the heap is. This tends to be important, especially in Android and other constrained situations. You can see when garbage collections occur. Is this the point of some of the jank that we have because we keep taking GC hits all the time? You can catch memory leaks. So if it's just growing without bound over time, how do we get that information? Usually there's another tool that you can use associated with that, so you can grab the whole heap and then find out all the things that are still referenced and not going away over time. And you can track allocations, and that's the part that we're interested in right now. When are things being allocated and why? And then we can backtrack it to call stacks and where in the code this thing actually happened. So I wrote this code all by myself. So it's a tight loop. It's going to run through this 10,001 times, and it's going to take this int value and set it to something that is a nullable int value. And we're going to see what happens. So in, again, Android Studio or IntelliJ, on the bottom left, you have this little button that says Run. But over to the right of that, you have the profiler thing. Oh, this is an Android Studio thing. Sorry, not IntelliJ. You click on profiler. It shows you different pieces of information about battery and network and memory and CPU. We're going to click on the memory one. That shows the heap over time. And then we can go ahead and drag the mouse cursor along there and say, I'm interested in this little block of time because obviously something interesting is going on there where we allocated a bunch of objects. So you select that, and then down in the bottom of the IDE, you see more information about all of the objects that were allocated in there. So if you look closely, it looks like there were a bunch of integers allocated, exactly 9,873, which is weird because in our tight loop, we were going through 10,001 times. So what is going on when 10,001 doesn't equal 10,001? So here was the code going up to 10,000, but those were the number of objects that were actually allocated. So it turns out if you look at the value of method, it uses a cache. When a process starts up, we automatically create a bunch of integers because we know that integers are really common. So we're going to go from what, negative 255 up to 256, or negative 128 to 127. We're going to basically pre-allocate a bunch of these objects so that we don't have to allocate on the fly. And then they're just sitting there in a cache. So when we grab one of those values, when we want to allocate one, we don't actually allocate it. Instead, we just reference one that already exists somewhere in the process. So that means we only needed to actually allocate the delta between that many in the cache and 10,001, which is, turns out, 9,873, if you do the math. All right, so if you click on one of these allocations, that was the one we were interested in. Where are all those integers being allocated? So you can click on that, and then you get more information over on the right, and you see every single one of the allocations. You'll click on any one of those, and you get the call stack. And you get information on the code where it actually happened. And then you click on that thing and you see, yep, that was actually my method where I was allocating all of those things because of the auto boxing that was happening.
All right, so that was just a very simple example to introduce the tools. Now we're going to look at more advanced features. So the first one we're going to show you is the when construct. It's the equivalent of the switch in the Java programming language. And more interestingly, when you switch over an enum. So this particular implementation, what the Kotlin compiler does here, is not specific to Kotlin itself. The Java compiler does the same exact thing, but it's still interesting to see how what seems to be a fairly simple language feature can turn into much more complex bytecode in the end. So here we have a simple enum that I've declared. It's called blend mode. It has 4 different values. And then I wrote a function somewhere in my code, and I switch over an instance of that enum, and I have all the possible cases, and I just invoke a function. It doesn't really matter what we do here. What's interesting is that we just switch over the enum, and we have the different cases. So if we look at the bytecode, we see this happen. So if you look at the top, it says get static, blending KT $when mappings $enum switch mapping. And if you look at the end, you can see the type of that value. So here we're getting a static field from a class that was clearly generated called when mappings. And the bracket I at the end tells us it's an array of integers. Then it invokes the ordinal method on the enum. And finally, it loads a value from the array we just fetched using the return value of the ordinal method. And then we have the actual switch happen. So what's weird is that there's this table that we didn't write in our code that just appeared out of nowhere. And then if you look at the branches themselves, when you look at the switch, for instance, when the case is 1, we jump to L3. L3 is one of the functions in my case. So if we decompile the bytecode of that when mappings class that were generated, it looks like this. So there's a static int array called enum switch mapping $0 that has the size, the same length as my enum class. And then I have a static initializer block that will fill this array using the ordinals of the enum, and instead of and the values are values generated by the compiler. So this happens to preserve binary compatibility when you add things to your enum, so that existing code can still work. So it's quite a bit of code that's added, and more importantly, every time you load your code, the static initializer will run, will allocate some memory and execute those few assignments. So let's look at what happens if we generate a second when. So here I wrote another function that does something different. It prints a value instead of calling functions. The when goes over the same enum values, they're in the same order, so it's exactly the same when as before. The cases are just different. If we look again at these when mappings, we can see that a second array was created. And if you look at the static initializer, this array is filled with the same exact values again. So really what's going to happen is every time you do a when in your code or switch over an enum value, you're getting a new array that has to be allocated when you load the class, and it has to be initialized by filling in those values generated by the compiler. And just for completeness sake, this is yet another example. So I have another when. This time I switch over the values of the enum in reverse order just to see whether the compiler does anything smart. It doesn't. It just adds yet another array that has to be initialized at class load time.
All right. Lazy is a pretty interesting feature in Kotlin. It makes something incredibly easy that's very common for people to handle. So it tends to be advantageous to not bother doing a bunch of work until you actually need it, especially if that work is expensive. Sometimes you want to avoid allocating a bunch of objects or calling a bunch of initializer methods, whatever it is. And we all tend to go through the same sort of boilerplate approach. We could have an integer that is, okay, I'm going to use a really stupid example, but there was a real example in our team.
We'll talk about it at the end.
That is not far from this. So let's say that we didn't want to allocate this object automatically and assign it. Instead, we want to wait until someone actually needs it, and that's when we'll do the work. So here's how we would do that if we were doing it manually. We might have a private variable that gets set to null, and then we have another variable that's actually going to be the property. And then when someone does a get on the property, we'll see if the underlying property is null. And if it is, then we'll assign, we'll allocate whatever we need to do, and then return that private. And then after that, it's already assigned. So all we do is return the private value. All right, so that's what it looks like in Kotlin, and then it compiles into the decompiled bytecode, basically does exactly what you'd want there. It's all pretty straightforward, right? So this is all good, but the automatic approach using Kotlin is even better. That's it, right? So you just say buy lazy, and then magically it just does that for you, right? Hopefully exactly what you did otherwise. Maybe it has a private variable somewhere, whatever. Not quite. So the way that it does this is, first of all, it starts out by creating an array of what are called k-property values. So since Kotlin has different capabilities in its properties than Java programming language does, then it needs a different way of accessing this stuff through reflection. And it does that through the k-property object. K-property is not just the Java stuff, but also other information that it needs for some of the Kotlin property capabilities. So it's going to use this mechanism in general for the general approach of delegation property delegation, which it's using for buy lazy. So it's going to allocate an array, first off, and then it's going to allocate a k-property object and stuff it in there. And the k-property object stores information about the class type, name of the variable, and the type. So there you go, one array allocated, one object inside that, and then it's going to create this lazy object, return that, and then that lazy object is going to be called to actually get the value at runtime. So that's going to be called, the getValue method is going to be called and return an int value from there. Now this is the part where it could be a little scary because maybe it's going to be using reflection to then call into the k-property. That is a very general mechanism that it can back off to for some property delegate situations, but they're a little more clever than that in the compiler, and they specialized it and said, okay, well, here's an extension method that we'll use instead. So if somebody calls getValue on a lazy object, then instead we're just going to return the underlying value. So it doesn't use reflection, uses the extension method instead, so all of that's good. But we keep going. This is where it actually figures out what the value is. So we have this method that it's going to call with a couple of conditions in there. And inside there is a synchronized block, which could be expensive depending on what's going on with multiple threads in your application. And then finally, here is the underlying bytecode to actually create a bunch of this stuff when it's instantiated. So whenever you have one of these lazy objects that gets initialized, then it basically runs all this bytecode, creates this array, creates the underlying k-property, and then every time you want to get the value, it's going through these sort of couple of indirections to get the information.
Yeah. So buy lazy can be extremely useful, but Chet mentioned that we ran into this on one of our projects. So someone on the team had a rectangle as part of one of the widgets for the UI Toolkit. And that rectangle is not used all the time, so they wanted to lazily allocate the rectangle. So, rightly so, they used bylazy. So bylazy, new rect. But then we looked at the generated bytecode, and so to avoid the allocation of a rectangle, which is just made of four floats,
four floats,
yeah, 4 floats or 4 ints, whatever, we were going through all that code, and more importantly, to avoid allocating that one small object, we were allocating an array, the key properties, the delegate, and so we are allocating more memory to avoid allocating a small rectangle. So bylazy is great, but only use it if what you're doing is actually very expensive. Otherwise, bylazy is going to be more expensive than what you're trying to save in the first place. All right, next up is unsigned integers. So unsigned integers are an experimental feature as part of Kotlin 1.3, and they're implemented with another feature called inline classes. I'm going to take a look at inline classes in a little bit. But the way you use unsigned in Kotlin, first of all, you have to turn them on. But when you use a literal type, you can just add this u suffix to say that you want an unsigned, and then you use them just like regular integers. So it's really nice. And if we look at the generated code, it looks exactly like integer. So if you use a 42 as an unsigned, it's just going to push the integer 42. Remember, the JVM bytecode or the class bytecode does not know anything about unsigned. Unsigned are not native types for Java bytecode. But here, we can just use it as an unsigned. Same thing for the next value, and then when we want to add them, it's going to call iadd. So it loads the first value A, it loads the second value B, and calls iadd. It is the integer add, and that works for all unsigned values as is. And then it invokes this static method called uint.constructor-impl. And if you look at the signature, it takes an integer as a parameter and returns an integer. Now, if we look at what that method does, it gets very interesting. So we have the method. It loads the parameter that you give it, and then it returns that parameter, and that's it. I have no idea whether the compiler generates that, but that's just extra code. That will probably, it will get jitted away, or if you use any kind of optimizer like ProGuard, it probably will get rid of it. But in the meantime, the compiler does too much work, and your bytecode has more stuff in it. So that's not a reason to not use unsigned, just an interesting thing that the compiler does not optimize yet. Other operations with unsigned are just as efficient. So we just saw that the addition uses the integer add. The same goes for subtraction. It uses isub. Multiplication is imul. And the division is the only thing that doesn't work the same between signed and unsigned. So they have to call a static method called uint_divide. That's more complicated, but you shouldn't have to worry about it. If you need to use unsigned in your code, by all means use unsigned because they have a very powerful meaning, and you shouldn't worry about the division here. So here's another example. So we're just going to take an unsigned in this variable called n. We're going to take a regular signed integer in variable z, and we're going to print the two of them. So let's take a look at the generated code. So let's start with the int one, which is the default one that you would see in Java. So just going to call print a print line of z. That's expected. But when you want to print a uint, an unsigned integer, it's going to call that method called box-impl. And you see it creates an instance of this class called uint. It's because uint overrides the toString method, and that's what println will use. Because println has an overload for integers, but it doesn't have one for unsigned integer. And because unsigned integers can represent more positive numbers than regular signed integers, JetBrains had to implement their own toString method. So just printing unsigned will cause you to allocate memory.
All right, ranges are interesting. I think the for loops are one of the most confusing things to hit people with if they're coming from Java or C or C++ or any of these.
And by most people, you mean you.
I do mean me, and other people I've heard of, also me. All right, so it's like I just didn't find the syntax I was looking for. Instead, there's many ways of accomplishing the for loop, just not the way that I was looking for. Instead, we have this concept of ranges, and we tell Kotlin very explicitly what is the range that we're actually looping through. So there's the for loop, where we say I in the following range, inclusive of the final value, or we could do the one that's exclusive of that final value, so we go until 10 instead of including it, or we could repeat a lambda a certain number of times, or we can do a for each call on a range. They kind of all look the same to me, off by one error, but otherwise they're kind of all very similar. So what do they look like in bytecode. So this one does kind of exactly what I was looking for. It does kind of how I would write it in the Java version of this. So it iterates through the loop, does the thing. This one, pretty similar. It just doesn't go up all the way. Repeat, same thing. But the last one, for some reason, it decides, no, I got to create an iterable and then call next on that thing every time through. So automatically, just for using one syntax versus the other, you're doing allocations and going through a bit more heavyweight approach. So it's not obvious to me why that happens, but it's kind of good to know that it does.
So by default with this syntax here, when you say for I in 0.10, you're going to increment the I variable by 1 every time you loop. Now, if you want to increment by something else than 1, let's say 2, you have to say step 2. But this can have a pretty big impact on the generated code. So if you just say step 2, the loop we just saw that looked exactly like the kind of loop you would write in the Java programming language now looks like this. So we create an int progression that takes an int range. Then we get the first, the last value, the step value, then there's a bunch of branches. We have an infinite loop with a terminating condition inside. So a ton of code gets generated. Again, just because you wanted to increment your loop by 2 instead of 1. And the worst thing is the compiler here is not being very smart. The only key for the optimization is the actual syntax you use. So if you write for I in 0.10 step 1, which is the same thing as not saying step 1, the compiler will still generate all that code instead of the nicely optimized loop that you would have written by hand. So most of the time, probably not a big deal, but if you write performance-sensitive code, you probably want to avoid this. So I mentioned inline classes earlier. That's how unsigned numbers are implemented in Kotlin. So inline classes can write a single field. So in this case, I created a class called color, and it takes an integer called C. Inline classes, the way they work, I mean, it's kind of in the name. What's going to happen is that at compile time, the compiler will get rid of the class itself everywhere it can, and will just access the field directly. So it makes it easy to create a new type in your code. It makes it easy to reason about that type, but you get the performance of just using, for instance, in my case, a regular integer, a primitive type. So I've also created several properties on that color class that just shift and mask bytes, so I can extract the red, green, blue, and alpha channels of that color object. And then we're going to start using that new color inline class in various ways and see what happens. So I created a print color function that takes a color instance, and then it just calls the different properties to access the red, green, blue, and alpha channels to just print them in the console. Here at the bottom, you can see my main function where I create an instance of my color class, and I just call the print color function. And this is what the code looks like. So first, we load a constant. So this constant 2131, that's the equivalent of the hexadecimal notation I have here. It doesn't really matter what the value is. Then it calls this static function called constructor-impl that takes an int and returns an int. That's very similar to what we saw with unsigned integers. And finally, it calls my print color function. But you can see it's not called print color anymore. It's called print color dash some kind of hash. Instead of taking a color instance as a parameter, it takes an I or an integer type. So it's nice, it works exactly as we wanted. The color class itself is completely gone. This constructor impl is exactly what we saw with the unsigned ints. It just takes the parameter and returns it, so it doesn't do anything. So we're only using the integer, the color class doesn't exist at all. There are some gotchas with inline classes. So here, for instance, I created 2 instances of my color class, and I want to compare them. So in one case, I call equals, which in Kotlin is the same, or should be the same as calling dot equals with more or less nullability taken into account. And then I call dot equals manually. So first, what happens when we call equals? So we load the first variable that we want to test with the iLoad. Then we call this invoke static method, and that static method is box-impl. It takes an integer and returns a color instance. So here we're boxing. We're allocating memory just for the purpose of comparing 2 integers. Then it loads the second variable, boxes it again, and then finally invokes a second static function called requal that takes 2 objects. So just to be able to compare our 2 colors that are just 2 integers, we've allocated 2 instances of the color class. If you call dot equals by hand, it's going to load the first variable. It's not going to box it, but it's going to box the second one, and it's going to call this equals-impl static function that can compare an integer or with an instance of the color class. So Inline classes can be super powerful, and they are mostly super cheap. But again, if you were to do, let's say, high-performance graphics, you're generating like large bitmaps, and for some reason you need to compare pixels inside a loop, you're going to be creating a lot of garbage and probably like triggering the GC over and over again just because you're doing a comparison.
The implementation of arrays depends on how you generated that array. So you can have code that looks really similar that's actually doing something quite different internally. So here we're using the int array of, and we give it some values. And in the Java class file side, you end up having kind of what I was looking for. It's just a primitive array with those values. Or you could say array of, but pass in the same values because type inference is really powerful in Kotlin, so it must be the same exact thing. Turns out it's not. It's going to be an integer array. We didn't explicitly say int array, and therefore it's not going to use primitive types internally. We could say int array with a lambda, and then we get what we're looking for. The advice here is basically give it more information about the type of the array, and it can do something more optimal internally. Extension functions are cool. There's some sort of surprising behavior there in terms of subclassing, superclassing. So I wrote this code all on my own. So there's a class called superclass. There's a subclass of it called subclass. We're going to create excuse me, an extension function called getIdentifier in both of these. So we're going to plug it into the superclass, and it's going to return the string super. And same thing for sub. It'll return sub. And then we're going to create some variables. So here we have a super instance. It's just going to be the instance of the superclass. Then there's a sub instance is an instance of the subclass. Then we're going to create sub as super instance. So it is a subclass, but it is told it is a superclass. So it's being cast to a superclass. And then we're going to call getIdentifier on each one of these variables. And then finally, we'll do a runtime cast instead. So in the first case, when we call superval, when we call getIdentifier on the superclass instance, what do you think it's going to return? I hear crickets. Somebody. All right. Super. All right. You obviously just wanted me to give you the information. So there you go. When we call getIdentifier on the subclass, it's going to call sub. And when we call it on sub as super instance, it's going to return super. And same thing for the last one. These are the ones that can be a little bit surprising because I created a subclass. So what's the deal? I'm calling getIdentifier. It should be the getIdentifier that is actually in the subclass. And it's because of how extension functions are implemented. So at the class file level, you actually have static functions which use types in them, and then it's going to resolve according to the type. So we have getIdentifier, static function that takes a superclass, and a different one that takes a subclass. So when I tell these things what type they are, that is the static function that it is going to call. Right? So that first one, when it calls getIdentifier on the super instance, then it's going to call the getIdentifier that takes a super. Same thing for the sub. And when I cast to a super, whether it's at runtime or when I define this variable, again, it's going to call the extension function that's associated with the superclass type instead.
Kotlin has this feature called default parameters. You can assign values to your parameters, and then when you invoke a function, if you don't specify the value for the parameters, obviously it's going to use the default values that you've specified. So here I have a very simple example. It's an add function that takes two floats and returns the sum of the two floats. And for a very dumb reason, I give them default values. So let's look at how this code gets compiled. So we're going to see a method called adder that looks exactly like the one we wrote, except we don't have the default values. So the way Kotlin handles the default values is this way. It creates another method called adder.default. It takes our two float parameters and adds two extra parameters. One is an integer and one is an object. I still don't know what the object is for. It's probably to make sure that the signature doesn't clash with anything else. But the integer is actually a bit field. And in that bit field, every bit set to 1 means that the parameter was specified at the call site. And you can see here we have different tests where we check was the first parameter set. If it wasn't, we use our default value. Was the second parameter set? If it wasn't set, we use our default value, and then we call the actual implementation of the function. So let's look at different ways to call this. So if I call adder without any values, the generate code would look like this. Sorry. The generate code will look like this. It's going to pass 0 and 0 as the parameters for the floats, since I didn't specify what they are, but the bit field is going to be equal to 3, meaning that both parameters need to use the default value. If I specify the first parameter, we're going to see my value 3 that appears at the call site, and then the bit field changes to be only 2, which means the second parameter is not specified. And we can do that for the second parameter and for 2 of them at the same time. So when you specify all the parameters, Kotlin will skip the expensive implementation that checks the bit field. So it's fairly simple, but when I saw that, and I saw that it's using a bit field, my first thought was, well, there's only 32 bits in an integer. What happens if we have more than 32 parameters? So I wrote that function. That's also not super useful. It has 33 parameters. So let's look at the generate code. It's not very different. What Kotlin does is add a second bit field. So for every set of 32 parameters that you have, it's going to add an extra integer and do more and more tests. It's more interesting than anything else. There's no big cost at compile time. Finally, coroutines. How many of you are familiar with coroutines? That would make my life easier. Less than. OK, so everybody's using Kotlin and is not using coroutines. Go learn coroutines, please. Anyway, so coroutines are a way to do easy concurrency. So this is a suspend function. So when you have a suspend function like this and you do something expensive like this 1 second delay, you're going to block. It's going to block the current coroutine. It's going to suspend the current coroutine, but it's going to let other code run instead. So I have this compute function that just prints compute and then waits for 1 second. And this is my main program. It first prints launching coroutine, then it launches an actual coroutine. This is the global scope.launch. It invokes my suspend function twice. And it prints that we're exiting the coroutine. And finally, we wait in the main function for 3 seconds to make sure that we have time to execute those 2 delays that are part of the compute function. So if we run this program, the output looks like this. So we launch the coroutine, it computes, then it computes again, then it exits the coroutine. The way Kotlin implements coroutines is actually very interesting because, again, there's no magic, right? It's running on the same JVM that you're already using or the same Android runtime on Android. Everything is done through generated code. So what Kotlin does, it generates a bunch of code, but the most interesting part is a new class that contains this function called invoke suspend. And that class has a field called label. It's highlighted here, and Kotlin will switch on that label. So basically, Kotlin generates a state machine, and each state of the machine corresponds to a possible suspension point inside the coroutine. So when we invoke that invoke suspend function for the first time, we're going to switch on that label. The label is 0 by default, so we're going to enter the first case. And we're going to switch the label to 1, meaning we're entering the first suspend function. And just under this assignment, you can see that we're calling my compute function, so coroutines.kt.compute. And if this function returns a suspended value, we exit the state machine. And that's exactly what happens when we invoke that delay of 1 second inside my compute function. We exit the state machine. Then at some point, somehow, Kotlin will invoke this invoke suspend function again, so we'll re-enter the state machine. And now our state, this.label, will be 1, so we'll enter this case, we'll advance the state machine to the label 2, we'll invoke compute a second time, we'll exit the state machine again, and I didn't show here, but there's a third state that's for printing the message that says we're exiting the coroutine. And to prove to myself that this is how it works, I hacked the bytecode. So this is the header of the invoke suspend function. It starts by invoking a static method. You can use a bytecode editor to inject bytecode. So here all I'm doing is I'm printing a message that says entering coroutine state machine and prints the current state of that state machine. If we run that code again, so that was the output we got originally. And if we run that code again with that bytecode hack, this is what we see. So we launch the coroutine, we enter the state machine in state 0, we call the first suspend function, then we re-enter the state machine with the state 1, we enter the second suspend function, and then we enter the state machine a third time, and finally we exit the coroutine. So again, Not a big deal. Using coroutines, it's fantastic. It makes your code a lot easier to write, a lot easier to read, but it will generate a large amount of code and quite complicated code. So, if for some reason you do care about the amount of code generated, you might want to think about launching coroutines.
So we heard about a bunch of stuff, how it works in Kotlin, some of which is more expensive than other features. But the real question is, should you care? Like, aren't modern runtimes, including that on Android, which started out as being very limited, but is much faster now, aren't they good enough to handle this stuff right now? In particular, like garbage collectors are pretty clever. Can't they allocate and collect without us having to worry about this? Isn't that why we got into these higher level languages to begin with? Absolutely true. So runtimes are much faster. They are pretty good at handling collections and allocations. It's not free, but it is work that is pretty fast and really beyond the level where you need to care in most situations. So allocation tends to be relatively fast, and then things can get collected, especially things like young generations and temporary objects. But it's always kind of good as engineers to actually understand what's going on so that you can make informed decisions when it actually may matter, and to consider whether the overhead in all cases is worth it. So Romain mentioned a couple of cases like high performance graphics, or in Android we think of like the code that we write in the framework as being the inner loop of applications. We absolutely avoid allocations there not because they're expensive, but because, well, if this is the inner loop, we don't want to be running this code on behalf of all of the clients, all of the applications sitting on top of us all the time, and then causing the GC to actually do work. Even if it's cheap, it is not free. So are you running it in an inner loop? And then you can make the decision about whether it actually makes sense in your case. And that is it. We do have some time for questions. We'd be happy to take some, but that was the presentation. Thanks. Anybody? Yes?
Is JetBrains going to do some optimizations?
Is JetBrains going to do some optimizations? Yes. Two things there. So first of all, right now, I think for Kotlin 1.4, they are busy rewriting the entire backend of the Kotlin compiler, which will be written in a way that will make it easier to implement optimizations. The current architecture of the compiler, my understanding is it can be difficult to perform optimizations that are beyond just a few bytecode operations in the vicinity of the code you're generating. The second thing that we're doing that's more specific to Android, but on Android we have a tool called R8. It's kind of like ProGuard, except it does whole program optimizations. So on Android, at the end, all your code, all your libraries live in a single APK file. It's just a zip file. So we look at the entire application at once, and we can apply pretty advanced optimizations by knowing exactly how you're using different APIs. So for instance, in enums, we can replace them with integers if we want, because we can see the entire application. We couldn't do that on libraries because we don't know how other clients of the libraries would invoke the API, so we can't touch the public APIs. But since we look at the final application, we can do whatever we want. So we have a team dedicated, first of all, at Google, they're working on the compiler helping JetBrains, and then we have a team dedicated to R8 to make our own optimizations. And of course, we talk to JetBrains a lot.
Our sense in looking at some of the implementations was this is the functionally correct thing for the compiler to do in this situation, and then there's always opportunity for optimizations once they can do more analysis of what's going on, and as long as they can do it safely and protecting the contracts of the code itself.
And of course, you always you will have your JIT or your ahead of time compiler, so likely they will get rid of some of those unoptimized pieces of code. But the way we see it, it's better to not have to do that at runtime. So if the compiler can generate better code, it's better for everybody.
Hi.
Is there, like Kotlin, as my understanding is, the Kotlin compiles to a lower version of the JVM. So is there some stuff in the newer JVM that would provide something where you need less code?
Right, so you're saying that Kotlin right now targets JVM 1.8 or 1.6, I believe, depending on the compilation flag. So are there things in newer versions of the JVM that Kotlin could take advantage of? I do not know. That's a very good question, but I don't know.
Yeah.
In general, is
Kotlin code running, in general, is Kotlin code running slower than Java code?
Right, so in general, is Kotlin code running slower? No, this is actually something we've looked at extensively because we have a lot of applications on the Android Play Store that are now using Kotlin, and we haven't noticed a fundamental difference in performance. Again, it depends on the features you're using and where you're using them in your application, but it's just like anything. Like if you have performance-sensitive code, you should profile it and fix it. It's just interesting to understand why it might impact the performance of your application. But in general, for most code, like if you're doing a click listener on the button, it doesn't matter.
It's also important to note that the things that we're looking at, except for the when implementation here, are things that are special about the Kotlin language that aren't supported in the bytecode. So the question is, how does it do that? And in some cases, there is a certain amount of overhead, most of which is insignificant at the level that we're talking about here. The rest of it just compiles down to exactly what you would write the code as in the underlying platform instead. So yeah, it should not be any performance difference for most situations, and then there's specific features where there's a little overhead. I think that's it. Thanks.
Right, thank you.